All right, welcome to Doozer shop. I talk so loud because my old camera, the microphone did not pick up very well when I was standing in front of the camera. It picked up just fine when I was standing behind the camera filming. But I used to speak louder when I was in front of the camera. So hence my loud introduction of welcome to Doozer shop. I don't have to do that anymore with the new camera. So welcome to Doozer shop. I haven't done an update video in a while. Been working on the Colchester lathe. I run into like a thought process of, well, this isn't that interesting, I'll hold off until I get more done or whatever to make a video. But enough of that. Let me go handheld. We'll show you the progress on the Colchester lathe. Colchester says, what do they say? Their advertisement slogan? Oh, the world turns on a Colchester lathe. You know, and that's kind of cool. You know, made in England, the whole British Empire thing. You know, used to circle the globe, whatever. All right, handheld. All right. So, if I can recap some... you guys may remember, you know, this is the part that started, well, it didn't start at all. You know, this is just sitting in here. I have my washer ground there for spacing, my washer there. That's just sitting in there. So that's the feed rod that goes through there. Let me show you what I got over here. So you remember I painted the inside the bed. That was awesome. I didn't show this. I had another setup of the apron over on the SIP jig bore on that angle plate, and I'll show you what I did. All right, this is a cluster. So this is inside, mind you. So to support the rocker box, you know, the handle would sit in here, long cross feed, and then it would go over and drop in here, which is, you know, a longitudinal feed along the bed. And to keep it from falling down, so Keith Fenner, who has the same lathe, he put a little bracket on the front that came down and would support the handle, the lever, and then it would come back. And it was like a U-shaped piece. So you can see these holes, 1, 2, and then 3, 4. That's what I drilled. I had the front surface up against the angle plate. So I got those 4 holes, and it was nice doing it in the SIP mill, jig bore, whatever you call it, because then I have these, you know, they're exactly from there, the center line of that to there is like an inch, I don't remember, 1.25 inches, 1.5 inches, some even inch fractional increment. And I think it's like an even increment there. So that I can do. So now you might notice, originally, and I think I covered this in the last video, I put those 2 holes in, that hole and that hole, and that was going to be for a little steel bracket, a plate, to go across to those that hole and that hole, a bracket, or I'm sorry, a steel plate, yeah, bracket plate, whatever, and have a bar go across. And the bar was going to keep the rocker box from hanging down too much. So I did both. The last video I did these side holes, 1, 2, 3, 4, and then I didn't show it in a video because I was in a hurry, and then I did the front holes. And I figure I can use the side holes for something else. Let me move my stool. Yeah, you remember when I did those two, and I faced this for no other reason, and there was kind of a lot of iron on the casting, and I wanted to get rid of a hump, and it was about 50 thousandths of humped up, excessive, superfluous iron. So anyways, back to this. So this is the half nut, and it's cast iron. It's 4 inches long, and I think it's a 1.25 inches, no, 1.5 inches, whatever, and 4 threads per inch. So, and I'll show you how this is all going to be done one hand. All right. So this joker, this half nut, it binds up, right? It kind of is sticky. And let me show you. Let me take it out. I put a spring under it too. Alright. Alright. So this half nut is guided by a 3/4 inch solid bar stock post. And I added a spring to try and it was an idea I had for, you know, to try and support it. So this thing works pretty well. You know, this is upside down. With gravity it works better, but it can still crook and bind. So let me set that on the stool here for a second. So it sits up against here, and there's a little angle plate that goes here, and it kind of, you know, rides in here. This angle plate was cast iron, and it had a crack in it. And I got it, I brazed it, and I was soaking it in a bucket of water to get the flux dissolved. But anyways, so this bar prevents engaging the half nuts when the power feed is also engaged. It pushes on here and whatever. It's kind of in the way for this video, but it just nests up there. So this shaft isn't backwards because I was test fitting something. But normally, okay. So what that is, the handle goes on that spline. That little flat is for the protection. The dog goes into that, milled out. That's the thing that keeps it from being engaged at the same time. But this is like a cam. So it's not concentric with the shaft, it's kind of offset, but that's not the cam part really. It's this little slot cut. What the deal is, let me kind of shuffle. The shop vac was in the way. So the way that this works, let me kind of get my, alright. To lift and lower the half nuts, and that's the guide rod, this cam, my knees are going to crack, okay. That's the cam that lifts and lowers. So that's lifted up and that's lowered down right there. See, yeah, and it stays centralized, so that's up, yep, and that's down. Now, the problem with this is it binds up because when it's up, the cam slot is essentially horizontal and it keeps it up. I mean, it's a smiley face curve, but it's essentially horizontal. So when it's engaged and the half nuts are down, touching the lead screw, that, you know, curve slot I mean, is always going to be curved. I mean, that's a given because that's the shape of it. But it's like when you twist this, there's a lot of sideways component. The component of the forces, the vectors, there's a lot of sideways thrust and not a lot of lifting up thrust. So that's how forces with the vectors are kind of situated. Until, I'm going to drop this one-handed, okay. Until it gets like that, and then it's cradled, and there's a lot of upward force because it's cradled sideways. But when it's like that, it has a heck of a hard time lifting this cast iron half nut up because of the side forces. All right, so the side forces, what it does, it makes it want to twist. All right, I'm going to set this down. All right, so it makes it want to twist. It makes it want to do this and this. Twist, twist. And that's a problem because it's sitting in there in the area where it sits, and it binds against, you know, the bearing area where the machine flat is, and then the angle plate that's not on there binds against it. So initially what I did was this. All right, I'll just lay that down on the stool. So this is all cast as one piece. This bar, this is like cast iron. This whole thing is cast iron. I made a bronze, a 954 bronze bushing. So that is threaded 3/8 coarse thread, and that's a 3/8 like steel stud. And I turned the end of it down to 281, which I think is 9/32. So this is bored like a 281, maybe a half a thou to a thou clearance. So instead of the lifting stud, you know, scraping, it didn't roll in here. It just was a scraping action. You know, at least I got a roller on it. So it does work. It rolls very well. It rolls just fine. So I'm stuck with that 3/8 diameter because that's the size of my trench, my smile, my cam. I guess I'm going to call this a cam. And I guess my bushing is a cam follower. So let me put this in. All right, you know, whatever. All right. Yep. I'm not putting in the spring. It was never there from the... So you can see there's a little bit of wiggle room there. So perfectly straight is that. Right? That's perfectly straight. The reason I know that rock, when that's touching, that's straight, is I got a little Moore and Wright Sheffield. Okay, it's even a British square. How sweet is that? British lathe and a British square. So that's square. I mean, that's touching that machine surface and that machine surface. So that's square. Okay. Okay. So I know that orientation is square. All right. So this, I'm going to try and get the light. There you go. I'll stand in my own light. So this is the cam. So there. Now this is how it works, okay? So all right. So now you can get that in the shot. I'm pushing down and it's coming there. It's up, down, up. So now it's easy. Now, well, I'm speaking backwards. It's upside down. So that's engaged. Let's talk engaged. So that's engaged, disengaged. Now I'm pushing down, and I don't like forcing it. There's too much force there. So there's not much. So like I said, that's good. It wants to disengage, but now, like I said, when you try to bring it back down, engage, the component of the forces is pushing this sideways, right? And it's you know, it's a fair bit of force. Maybe it's all right, but I'm thinking, and I don't know, I'm just kind of thinking here before. I've never used this lathe because it had the broken gear. It's the broken gear. Ooh, boom. Now it's the new gear. Boom. I'm wondering if these half nuts, once they're okay, they could be hard to engage or hard to disengage. So they're disengaged now, and like I say, this is upside down, so gravity is helping me in the other, you know, because this apron's upside down on the bench. So I'm trying to, so that's in engagement. So maybe pulling up is not bad. I don't know. Maybe I'm worried about this for nothing. I have thought of that. Maybe I'm just absolutely crazy. And I'm an engineer, so I'm obsessed with making things better. So, yeah, there's my knees. So what I thought is I'll put that spring on the post and help it go down. I mean, this is, again, upside down, and gravity's going to help it. But I just don't want this thing to be hard to engage and hard to disengage. Because if you're running, let's see, the screw, so that's the headstock. The headstock is that way. So your screw, when you're winding and engaging, the force of the screw is pushing that way. So the screw is anchored at the quick change box. So the screw is in, let's see, tension, and it's pulling it in that direction. Okay. Yep. So, like I said, maybe I'm worried about this for nothing, but it seems like a pain in the butt. If there's no oil on there, it's a bear. So anyways, my thought is this, okay? Sit down here. Because this half nut wants to rotate, because it's constrained in this way. It's constrained this way, but not in the rotational aspect of it. It's constrained a little bit there. I mean, so it's pushing from there. So the post is kind of right under the center of that. But the thing is, if you draw a line from there to there, how can I explain this? You're not pushing exactly perpendicular to the line of force. See, if your post is there, underneath, you know, it's all directly underneath. So assume that this is your post, right there. And you draw a line here that comes out at like a 20-degree angle, and then you're pushing in. So your line of force is not perpendicular, or to say 90 degrees. If your axis of rotation is right there, because your post is there, and you had something to keep the half nut from going in this way and in that way, then you would be constraining the force, you know, the forces 90 degrees perpendicular to the axis of motion, because it's right along this axis, and that's where it'd be hitting. If you're touching here, you're drawing an angle over to there, and then you're hitting. And you know, if that angle's 45 and the angle's 45, your line of force is at 45, and that's going to bind. It's going to put a pushing force, right? If your line of force from this rotational point to here where it hits against that solid surface, you're not coming in and hitting dead square. You're coming in and you're hitting at an angle, and then it's forcing, it's putting some compressive forces in there. And it's pinching. It's pinching against here. It's creating a pinch bind. If your rotational axis is here and you're going to put a bumper stop here or here, you're hitting straight 90 degrees and it's not binding. There's no crosswise compression because you're absorbing the force of rotation 90 degrees to the axis of rotation. If you're absorbing it here and you're pushing there, you're getting some compression, what's going to put it into a bind, because it's going to start pinching against that, because you're coming at an angle and it's wedging. It's like a wedge, like driving a steel wedge underneath the bottom of a door. You're wedging. So this way, you have no taper, no angle. It's just straight on. Be just like, you know, rolling a pencil underneath the door. It's flat. It's not going to catch. It's not wedged up where it's an inclined plane. So this is an inclined plane. It's going to wedge. Straight up, it's just like pushing something against the corner of a wall. It's just there. It's not going to wedge. You can pull it back easy, right? If you push a box up against a wall, you can pull it back. If you drive a wedge under a door, it's has an angle and it's going to jam. Okay, so that's about engineering, like force vectors. So I thought about putting some kind of bumper in here, and this is kind of open, and maybe, I don't know. Another thing I thought, instead of pushing against something here and pushing against something here, what I could do is, because my axis is right there, instead of absorbing it, like pushing there or pushing there, what I could do, look how meaty. This thing's pretty beefy. I could drill and put a pin in there, a 1/4-inch pin, Loctite maybe even, heck, I could do a 3/16 or even an 1/8-inch pin. Now I'd go bigger than 1/8. Say a 3/16 pin. And the pin, and let me kneel down. Alright. If the pin came out then it would be 90 degrees. When this thing rotates, imagine a pin sticking out, straight out towards the camera. Boop. If you had, because this goes up and down, right? You know, you can see there's your axis of rotation. Is the stub shaft. If you had a pin coming straight out, and this angle plate, which is not there, had a slot in it, so this was still free to go up and down, and the travel's 1/2 inch. It goes up and down 1/2 inch. So if I have that angle plate and I put a dowel pin in there and I slot the angle plate, then it could not rotate. That pin would keep this half nut from rotating in the slot, in the vertical slot in this angle plate, which you don't see. And then again, it would be no wedging. It would be purely absorbing the rotational on a straight on 90 degrees to that axis, or perpendicular. So I could put a pin and hell, I could even slot this with an end mill. I could put a blind slot in here and put like a little screw in from the angle plate. Number of things you could do. And what that's doing is it's absorbing the side force created by that lifting cam. So that's a lot of messing around. So another thing I thought of, let me give you a good camera angle, is this. Alright, get rid of that. Alright. So there's plenty of room in here for something. And I thought, you know what? You could, instead of having this being a cam, turn that into a half of a crankshaft. Right? Just an offset pin. So picture this, instead of a slot, there's the center. Just have a crankshaft, a pin coming out with some kind of stroke. Like I say, this comes up and down exactly 1/2 inch because I measured it with an indicator. So there's a pin coming out of here, and it's threaded and Loctited with blue Loctite. I can get that out with some heat and scrap that pin and put a longer pin out and a connecting rod and another pin coming out of here. And I thought about little ball bearings and such, but I don't even think you need ball bearings. As much as load as it would carry, just a bronze bushings would work. So we had a 3/8 stud pins, whatever, sticking out there, a 3/8 stud pin sticking out there, offset from the center by 1/2 inch, and make a little connecting rod between the two. I could make it out of solid bronze or whatever. That's an idea. So then it would be a crankshaft. So if you know a piston on a connecting rod on a crankshaft journal, it reciprocates and goes up and down, but you can't rotate it and twist it because it's on bearings, bushings, the connecting rod bushings. So this with a connecting rod and an offset pin, you couldn't have that. It would be locked in. It'd be putting twist in the connecting rod, and it'd all be the torques and the forces would all be absorbed by the shaft and everything. I think that would work. So that's my thoughts with that. I'm thinking about doing a connecting rod there. Okay. I talked that to death. Sorry. But that's where I'm at. So this is pretty cool. So this is upside down, mind you. So there's a, might be able to see. I got some pipe cleaner wick in there. That's the oil journal. Like I said, this upside down. So there's an oil passage drilled in there. Goes, there you go. So oil drips down there through this passage and it lubricates that bushing for the gear. So I cross drilled the shaft, I end drilled the shaft, put a plug in it, and you can see what I got. You see, yeah. Try and get the camera, bear with me. There's a 1/16 hole there, right? There's another one there for oil. So 1, 2, I got 4 of them. 3, 4. So oil comes, it picks oil up from here in the bushing, and is end drilled. I got a 1/4-20 Allen grub screw, set screw to plug the port passage in the center of the shaft. And we got those in there for lubrication. So that gear that meshes with the rack and drives the carriage is lubricated. So that's where I'm at with this. Maybe leave your comments if I should do the crankshaft thing. Until next time, this is the update from Doozer's shop.